Interior of the Earth. Today we are going to study about interior of the Earth, that is Earth's layer, the internal structure of the Earth, the crust, that is atmosphere, the mantle, outer core, inner. Within that, we have to learn about abundant elements of the Earth's crust, most abundant elements of the Earth, lithosphere along with the asthenosphere, and seismic discontinuities also. Interior of the Earth's most abundant elements of the Earth's crust are oxygen, silicon, aluminium, iron, calcium, then sodium, potassium, and magnesium. Oxygen occupies the maximum part, nearly half of it, that is 46.6%. Most abundant element, that is chemical composition of the Earth, is iron, oxygen, silicon, magnesium, nickel, sulfur, and titanium. How will you understand about the interior of the Earth? It is not possible to know about Earth's interior by direct observations because of the huge size and the changing nature of its interior composition. It is an almost impossible distance for humans to reach till the center of the Earth. The Earth's radius is 6370 km. Through mining and drilling operations, we have been able to observe the Earth's interior directly only up to a depth of few kilometers. So, through some direct and indirect sources, the scientists have a fair idea about how the Earth's interior look like. The Earth is primarily made up of rocks, metals, water. The surface is solid, but its interior is composed of molten matter due to the intense heat it experiences. Solid earth on top, interior we are having molten matters. Sources of information about interior of the earth. Direct sources. Surface rocks. These are the most readily available solid earth material to make direct observation. Laboratory experiments on surface rocks and minerals provide important information about interior of the earth. Mining. Through analysis of rocks collected at different depths gives us information about Earth's interior. Through mining and drilling operations, we have been able to observe the Earth's interior directly only up to a depth of few kilometers. World's deepest mining is limited only to the depth of fewer than 5 kilometers. Going beyond this depth is not possible due to excessive heat at this depth. Here we can see the mining excavation is going on and it is collecting the rock materials. Deep ocean drilling projects. Scientists have undertaken some major projects to penetrate the surface of ocean to access the conditions in crustal portions. The deepest drill at Kola in the Arctic Ocean. Mind it, the human being cannot reach over there, but it has been drilled. So totally it is machinery activity. A depth of 12 km and other deep drilling projects have provided information about the conditions in crustal portions through the analysis of materials collected at different depths. Volcanic eruptions. Volcanic eruptions forms an important source of obtaining direct information through laboratory analysis of the molten material that is thrown onto the surface of the earth during a volcanic eruption. However, it is difficult to find out about the depth of the source of such magma. Volcanic eruption through that we can get the lava which is coming out from the magma chamber from inside the earth, as well as the pyroclastic materials, the boulders, the rocks which is thrown out from the interior of the earth on the earth's surface. That also gives us the idea about interior of the earth. Indirect sources of information. By analyzing the rate of change of temperature and pressure from the surface towards the interior, meteors, as they belong to the same type of materials Earth is made up of. Gravitation, which is greater near poles and less at the equator. Gravity anomaly, the reading of the gravity at different places is influenced by many factors. For example, distribution of mass, distance from the center of the earth. Such a difference is called gravity anomaly. Gravity anomaly gives us information about the distribution of mass of the materials in the earth's interior. Magnetic sources. Magnetic surveys provide information about the distribution of magnetic materials in the crustal portion and thus provide information about the distribution of materials in this part. Seismic waves. Seismic activity is one of the most important sources of information about the interior of the earth. After analyzing signals from seismic waves as they pass through the earth, scientists have come to know about the state of the interior of the earth. Body waves, that is a specific body waves generated by an earthquake, especially air waves, which travel only through solid material, helped in understanding the state of materials in the interior of the earth. Here, the meteorite or meteoroid, which is touching the earth as meteorite, it is actually the same type of material earth is also made up of. Even the seismic waves, the P waves and the S waves. We know that earth has different layers because P waves refract and create a shadow zone. Refraction could only happen with different layers. S waves cannot cross or it cannot pass through the solid material. So in that case, we are getting the shadow zone over here and we are getting the information about the state of matter within the earth's crust or interior of the earth. Structure and composition of the earth. The interior structure of the earth is made up of three main shells. The very thin and brittle crust, the mantle, and the core. Inner core, outer core, mantle, and the crust. Mantle is divided into two parts, inner mantle, lower mantle, and upper mantle. Crust is also divided into two, continental crust and oceanic crust. Core is divided into two, outer core and inner core. 15% of the Earth's volume is occupied by the core and 84% occupied by the mantle and 1% is occupied by the crust. Here we can see the layers of the earth: continental crust, oceanic crust, lithosphere, asthenosphere. Actually, lithosphere is containing these all the three of it, that is the continental crust, oceanic crust, and the asthenosphere. Asthenospheres is the upper part of the upper mantle, and below the upper mantle we have the lower mantle. Together it is called mantle, upper mantle and lower mantle. Together it is occupying the largest portion of the interior of the earth. And then we have outer core and solid inner core. Crust. Due to its accessibility, we have good understanding of the structure and composition of the earth. It is the skin of the earth, outermost solid part of the earth, brittle in nature, thinnest layer, depth is 35 to 60 kilometer below continents and 5 to 10 kilometer below the oceans. Temperature 0 degree to 870 degree centigrade. Density is 2.7 gram per centimeter cube to 5.5 gram centimeter cube. Nearly 1% of Earth's volume and 0.5% of Earth's mass. The crust of the Earth has two distinct divisions, that is the continental crust, CL, oceanic crust, CIMA. CL is much thicker in the areas of major mountain ranges extending up to 70 km in the Himalayan region. The discontinuity between the oceanic crust and continental crust is termed as the Conrad discontinuity. Interior of the Earth. Continental area much thicker, that is the upper continental crust. The other surface the rock. It is above the oceanic crust. Oceanic crust is the more thinner. The discontinuity is between the upper crust and the lower crust. And in mantle and crust, that is the lower crust, with orogenic discontinuity. Upper crust, that is the continental part, whereas below that, getting the oceanic crust. Actually, the continental crust is floating of the oceanic crust. Continental crust is thicker, 55 to 60 km. Oceanic crust is much more thinner, 35 to 10 km. Density of upper crust is centimeter cube, whereas lower crust has 3 centimeter cube. Composition of the upper crust, silica, aluminium, that's why it is called sea. Actually, it is mainly composed of granite rocks. Lower crust contains silica and magnesium, hence it is known as sima, mainly composed of basaltic rocks. Though these two layers, that is solid layer of the crust, upper crust and the lower crust, they are solid in nature, but the lighter CL is considered as floating on the denser sima. This arrangement of CL floating on sima forms the basis of Wegener's continental drift. Here we can see the drifting of the continents and the supercontinent Pangaea or Pangea. The composition of the crustal layer is important for us because we get most of our minerals from the crust of the earth. Presence of soil layer for the growth of both cultivated and natural vegetation. The physical features of Earth's crust influence land use and other human activities. The density of human population also depends on the nature of the relief features in an area. Wegener's theory. The theory of plate tectonics is now well established. Continental drift is happening as tectonic plates move from each other or towards each other, with earthquakes and volcanoes often occurring around their edges. Alfred Wegener proposed the theory of continental drift at the beginning of the 20th century. His idea was that the Earth's continents were once joined together but gradually moved apart over millions of years. It offered an explanation of the existence of similar fossils and rocks on continents that are far apart from each other. But it took a long time for the idea to become accepted by other scientists. Here we can see South America and Africa, they are nearly are attached. This picture, India, Antarctica, Australia, they were together was forming a huge, a giant continent, southern continent. The lithosphere, the uppermost polar solid brittle layer means rocks. Lithosphere means rock sphere and is derived from the Latin word lithos meaning rocks or stones. Its thickness ranges from 10 to 200 kilometer because it is also including upper mantle's part, that is asthenosphere, also in it. The lithosphere is broken into tectonic plates, that is the lithospheric plates, and the movement of these tectonic plates cause large-scale changes in the Earth's geological structure, that is folding and faulting. The source of heat that derives from the interior of the Earth drives plate tectonics is the radioactive decay of uranium, thorium, potassium in Earth's crust and mantle. It contains two types of rocks, granite and basaltic. Asthenosphere. Some tens of kilometers deep in the earth, the brittle lithospheric rocks gives way gradually to a plastic or soft layer named the asthenosphere. It is the main source of magma that finds its way to the surface of the earth through volcanic eruptions. The word astheno means weak. It lies below the lithosphere. The asthenosphere in between 80 to 400 km is a highly viscous, mechanically weak and ductile. It is the layer over which lithospheric plates or continental plates move, that is the plate tectonics are taking place. You can think of lithosphere on top of asthenosphere as the hard brittle shell floating on soft plastic underlayer. Interior of the earth, Morovisic discontinuity. It is the boundary between the earth's crust and the mantle. It was first identified in 1909 by Andrija Morovisic, a Croatian seismologist, when he observed the abrupt increase in the velocity of earthquake waves, especially P waves at this point. Here you can see P waves directly from crust one part to the another. It is 7 km per second. But when it is going through the mantle, it is 8 km per second. That means increasing the speed of it. The more basic discontinuity is about 5 km below the ocean floor and 30 to 50 km beneath the continents. The Moho is deepest beneath the Tibetan plateau, where it is approximately 75 km below the surface. We know that Earth has different layers because P waves refract and create a shadow zone. Refraction could only happen with different layers. Here P waves directly passing, but when it is passing to different sphere or layers of the earth, that time its speed decreases or increases according to it, and we are getting the shadow zone of the P accordingly. The mantle. Our knowledge of the upper mantle, including the tectonic plates, is derived from analysis of earthquake waves, heat flow, magnetic, gravity studies, and laboratory experiments on rocks and minerals. It extends from more basic discontinuity to or more discontinuity with depth of 299 2,900 km. Its main constituent elements are 45% oxygen, 21% silicon, and 23% magnesium. Temperature range approximately 200 degrees centigrade at the upper boundary to approximately 4000 degrees centigrade at the lower boundary. It has an average density varies from 3.3 to 5.5 gram per centimeter cube. It has portion of the mantle which is just below the lithosphere and asthenosphere, but above the core is called mesosphere. Lower mantle comes under mesosphere. The lower mantle is in solid state because of the pressure from high above. The mantle makes up about 84% of Earth's volume and 67% of Earth's mass. It is divided into upper mantle and lower mantle. Because of the temperature difference, there is convective material circulation. Here you can see in this particular diagram, in this particular image, the convection currents are forming, and above that, the continental crust or oceanic crust, they move. Here on the map, the movement of the sea floors and the continents are shown, resulting motion of the tectonic plates. This particular convectional current results in the movement of the tectonic plates. Temperature increases from Earth's surface to the inner core. First, it is very slow, the rate is slow, and after that, it increases. Again, the rate is nearly slow, means much more slow. Again, it increases depending on the material the area is containing. Core. The earthquake wave velocities have helped in understanding the existence of the core of the Earth. The innermost layer, about 3500 km in radius, that is outer core and inner core together is forming 3500 km in radius. It is separated from the mantle by Gutenberg discontinuity. It is the densest layer of the Earth. Its density ranges between 9.5 to 4.5 gram per centimeter cube, and sometimes it is written 15 gram per centimeter cube or 13 gram centimeter cube. The core consists of two sublayers. It is made up of very heavy material, mostly constituted by nickel and iron, and hence it is also known as Ni. Ni for nickel, Fe for ferrous, that is iron. The core makes up about 15% of the Earth's volume and 32.5% of Earth's mass. The core of the Earth is also called barysphere. The temperature at the center is estimated to be 6000 centimeter, maybe due to the chemical reactions under high pressure and disintegration of radioactive materials or radioactive elements. At 6000 degrees centigrade, this iron core is as hot as the Earth's surface, but the materials at the center of the Earth are in solid state. that is the inner core, because of the heavy pressure of the upper layers caused by gravity prevents it from becoming liquid. Dynamo theory suggests that convection in the outer core combined with the Coriolis effect gives rise to Earth's magnetic field. The two cores are outer core and inner core. Outer cores liquid or semi-liquid in state, not under enough pressure to be solid, so it is liquid or semi-liquid even though its composition is similar to that inner core. Its density is 5 gram per centimeter cube. Inner core solid state. The crushing pressure of upper layers caused by gravity prevents it from becoming liquid. 13 gram per centimeter cube or 14 gram or 15 gram per centimeter cube. Here we can see the magnetic field of the earth, and south magnetic pole was nearer the north pole, that is the geographic north pole, and north magnetic pole is nearer to geographic south pole. Accordingly, the compass direction shows north-south of the compass. North pole of the compass will face the south magnetic pole, and south pole of the compass will face the north magnetic pole. Seismic discontinuities. Seismic discontinuities aid in distinguishing divisions of the Earth's interior, that is, inner core, outer core, lower mantle, upper mantle, and the crust. Conrad discontinuity. It is in between the upper crust and the lower crust. Morovisic discontinuity in between the lower crust and the upper mantle. Repeated discontinuity in between upper mantle and lower mantle. Gutenberg discontinuity between lower mantle and outer core. Lehman discontinuity between outer core and inner core. Morovisic discontinuity, here it can be detected by a sharp increase in the speed of earthquake waves, especially P waves. Gutenberg discontinuity, it is located at a depth of about 2900 km. In 1913, German geophysicist Benno Gutenberg was the first to discover the approximate transition zone of the mantle and outer core boundary. Now it is known as Gutenberg discontinuity. Here seismic waves slows down, indicating a zone between the semi-rigid inner mantle and the molten iron-nickel outer core. Gutenberg also published many papers on semi-seismic waves with Charles Richter, who developed the Richter scale that measures earthquake intensity. Now, the difference between Morovisic discontinuity and Gutenberg discontinuity regarding the seismic waves, that in Morovisic discontinuity there is a sharp increase in the speed of earthquake waves, whereas in Gutenberg discontinuity it is slowing down. That is, the seismic waves slow down their speed. Temperature, pressure, and density of the Earth's interior. Temperature. A rise in temperature with increase in depth is observed in mines, deep wells, along with molten lava erupted from the Earth's interior. Temperature within the Earth increases with depth at a rate of 1 degree centigrade for every 32 meter depth, giving an Average temperature about before it was told 5,000, but at present scientists say it is 6,000 degrees centigrade at the center of Earth. Actually, it varies from 5,000 to 6,000 degrees centigrade. It assumes that the rate of increase of temperature beneath the surface decreasing towards the center. Now, rate of the increase of temperature is not the same as increase of temperature. Temperature always increases from the Earth's surface towards the center, but the rate differs. Pressure. Just like temperature, the pressure also increases from the surface towards the center of the Earth due to huge weight of overlying rocks. Density. Due to increased pressure and presence of heavier materials like nickel and iron towards the center, the density of this layer also goes on increasing towards the center.